Hello, everyone. Can you hear me okay? Thank you so much for coming to our talk, CUDA Grâce, Owning AI Cloud Infrastructure with GPU Exploits. Sam and I are part of IBM X-Force Offensive Research, and we're a security research group dedicated to vulnerability research and exploit development. We're super excited to be here today because this is actually our first presentation as a group, and we feel super privileged to be able to do it on the Hexacon stage. I first want to talk about research motivations, why we picked NVIDIA GPU as a vulnerability research target. This being our first project as a group, I wanted to pick something that was not only compelling, but also would have a high likelihood of success for team morale. My first reason was what everyone's talking about, and what you're probably sick of hearing about, AI. Whether or not you're bullish on AI or believe in it, its explosion is undeniable. And that expansion is going to need to be fueled by more compute, hence more GPUs. The second was Pwn2Own's inaugural AI category. We've had some talks about it here at Hexacon, but Pwn2Own had added new AI infrastructure targets. So a bit of competitive motivation and winning some cash wouldn't hurt. And even though NVIDIA is a massive player in the industry, there's still not been very much security research targeting its products, in particular, not very much binary exploitation research. So what is CUDA? It's in the talk title. You've probably heard about it before in relation to GPU acceleration. And it's NVIDIA's proprietary parallel computing platform and programming model. It provides compilers, libraries, and the API for GPU programming. It allows developers to code in programming languages such as C, C++, Python, even Fortran. Therefore, they can take advantage of the performance benefits of GPU acceleration. Now, to give proper context, I first need to explain the NVIDIA AI ML technology stack. The Pwn2Own target that we've looked at first is the NVIDIA Container Toolkit. And GPUs are complex. Setting up environments for GPUs can also be complicated. So NVIDIA built the NVIDIA Container Toolkit to allow cloud providers, enterprises, and developers to easily run GPU-accelerated workloads seamlessly across a variety of infrastructure setups. The way this works is that the AI ML workload, all the way at the top there in blue, it could be an AI model training job, a model inference training, inference job, or really any program that utilizes GPU acceleration and runs as an application inside a container. The container environment is configured with exactly the tools and libraries it needs for your workload to run, and the NVIDIA Container Toolkit integrates with any container runtime. It could be Docker, CRIO, Containerd, even Podman, which was a new one to me before this. And the NVIDIA Container Toolkit works alongside the container runtime to ensure that the containers have access to the GPU devices, the drivers, and the CUDA libraries, enabling them to fully utilize the GPU. And underneath the container layer is the kernel layer, which sits the host kernel as well as the NVIDIA GPU drivers, and those drivers talk to the GPU hardware itself. Now, the threat scenario that Pwn2Own wanted to emulate is AI/ML application compromise. So given a malicious container, the container's job is to escape and demonstrate execution on the host. And there's actually a ton of advantages of escaping the container from the kernel. The first one is that the container runtime doesn't matter. So we had some questions for ZDI, the organization that runs Pwn2Own, about whether what container runtime is eligible. Well, escaping via the kernel means it doesn't matter. And the more interesting one is that container hardening is completely bypassed. You can harden a container by running it as a lower privileged user. You can apply seccomp filters or lowers its capabilities so that certain kernel subsystems that are notoriously buggy, like netfilters or IOU ring, are not accessible to the container. But by definition, it needs GPU access. That's kind of the whole point. So the NVIDIA GPU drivers are always reachable. The other main benefit is that it doesn't matter, you don't need control over the container image itself. So Wiz Research, that did some excellent research on the NVIDIA Container Toolkit, actually found a vulnerability in their exploit, but their exploit required having control over the container image, which kind of limits the threat scenarios that it applies to. There's also some cons, though, mainly that kernel exploits can be complicated depending on the primitive. They can be unreliable, and usually more exploit development labor is required to target multiple kernel versions and defeat various mitigations. So at this point, we were really leaning towards going to the kernel avenue, but we wanted to get a preliminary impression of the code base. There are some things that stood out to me while doing preliminary scan of the code. The main thing, there was a lot of entry points for the user mode to interact with the kernel. The second was interaction via multiple subsystems, which when subsystems manage their own state, it can create some hidden dependencies across subsystems. So that can lead to like logic privilege bypasses or invalid state transitions. Another concerning thing that I saw, which I turned out to be correct about, was the use of mixed locking types and complicated concurrency mechanisms. And when concurrency control is overly complex, that means the developer is more likely to make a mistake. And a mistake in locking or concurrency can mean race conditions or time of check, time of use bugs. And there were enough red flags that I was pretty sure there would be some easy wins here. We were on a pretty tight timeline. From the time we started, we had exactly 4 weeks to the registration timeline, so I had to make a emergency hardware request to get an actual GPU because unfortunately drivers don't run without the GPU, and we got the laptop that was going to be used in the contest. We decided to go with Syscaller to do a fuzzing campaign because it looked pretty straightforward to set up, and it supports fuzzing out of tree drivers. With that laptop, we set up GPU pass-through with VFIO on a QEMU KVM VM, and Syscaller did fuzzing on that VM. And to test crash reproducers and to do exploit development and debugging, we used Azure Cloud instances with a dedicated GPU. To get Syscaller working with the NVIDIA drivers, we first needed to compile the drivers with instrumentation. In order to do this, we compiled our own Linux kernel, enabled instrumentation like KCUV, KSAN, KTSAN, and then ran the driver installer on the target, which compiled the drivers and linked them against our kconfig of our custom kernel. GPU drivers are stateful, meaning that you have to get it in a specific state in order to reach certain parts of the code. And to deal with this, we used what are called resources and pseudo syscalls. And these are syscaller features that allow these are Syscaller features that allow to model complex kernel interactions. So resources allow Syscaller to track and reuse kernel objects across multiple syscalls, like file descriptors or device handles, and pseudo syscalls allow us to define setup or tear down sequences, like scripting multi-step interactions that would be impossible to do with a singular syscall. We iterated getting more coverage using the KCUV report, so it told us exactly what lines of code that we were hitting, improved our definitions, and then got more coverage and worked cyclically like that. We did experience some challenges fuzzing with Syscaller. The first being that we only had one GPU in the laptop, and we were limited to one fuzzing VM per physical GPU. So we were limited by our hardware, which wasn't very powerful, and we couldn't utilize our cloud resources to fuzz either because of limitations on GPU virtualization. The other one was statefulness. The resources tracking system doesn't enforce the logic or order of syscalls. It only increases the chance that that ordering may be correct. Just an example, using sockets, Syscaller might generate an order of syscalls like socket, bind, listen, but it just as easily could generate socket, accept. It doesn't know that like semantic constraints, like you must call listen before accept. It only knows that they both take a socket FD as a parameter. In other words, the resource dependency model doesn't explicitly encode order. Another major issue that we hit was parasitic coverage. This is a known weakness in KCOV. KCOV logs instruction pointers and saves them inside of a buffer. So things like loops or recursion can easily overflow that buffer, and Syscaller doesn't have an easy way to adjust the size. And in any case, when you hit a large loop, it's mostly going to overflow. And since Syscaller chooses inputs based on coverage feedback, it favored these overflowing state cases instead of the ones that actually set up the state correctly. And this resulted in a lot of wasted executions, which is especially painful for us since we are already running slow on fuzzing. None of these issues were insurmountable. This could be fixed with more compute and dead time. For example, we could have fixed parasitic coverage problem by using a coverage filter, and that could eliminate certain instructions and lines of code from being recorded, making it less likely to overflow the buffer. But because of the short time frame for point-to-own, we didn't get to do that. The result was that we found several bugs manually while writing Syscaller definitions, and then we modified our fuzzer so that it would find those or fuzzing definitions, so it would find those vulnerabilities. We missed the point-to-own registration deadline by just a few hours after confirming the exploitability of a couple of bugs, but ultimately that was okay because, as you'll see in a second, the exploitation was pretty complex. We spent our remaining research time on exploit development and experimenting with the threat model and proving impact, and we tailored our exploit for Azure serverless compute. Great, we wrote an exploit for an NVIDIA GPU driver. We'll cover vuln and exploitation details here in a minute, but I first wanted to cover why this matters. Well, there are a variety of impacts, but arguably the biggest one is in the cloud. We've seen an explosion of specifically GPU cloud providers, with multiple dozens of providers entering the market in the last few years. And cloud providers, having seen the explosion of AI, have begun offering AI ML as a service in the cloud. Providers have serverless offerings where the customer can build, train, deploy models in the cloud without having to manage any servers. And the cloud provider handles setting up the AI GPU environment and maintaining the infrastructure. For the enterprise customer, this means better efficiency, less things to deal with, faster time to get to market, which in today's climate, especially when it comes to AI, can mean make or break. With these proprietary models in the cloud, these are high-value workloads that are sitting there. So it's especially important to consider cross-tenant attacks when thinking about this, where multiple cloud customers run on the same compute node. Now, what are cross-tenant attacks and what do they look like? Well, it begins by an attacker running, getting code execution in the AI ML container. This can happen with supply chain, malicious container image, remote network-facing service, or local, compromising a data scientist or a CI/CD pipeline. Then, from within the container, it exploits the GPU driver, getting kernel code execution and escaping the container. Then the whole node is compromised. From there, the attacker is now free to steal data from co-located workloads. Interesting data to attackers might be model weights, training and user data, and operational secrets like credentials. The central issue is containers as a boundary, where multiple customers are running on the same compute node, which makes one kernel bug a cloud-wide problem. Serverless functions and container offerings by AI cloud providers are common, and they depend on containerization as an isolation boundary. Why do providers choose it? For one, it's cheaper for both the provider and the customer. It's a faster startup for the workload and better GPU utilization. It depends on OS-level containerization like namespaces and C groups instead of a stronger boundary like hypervisor. Ultimately, the shared kernel means shared risk. any of the drivers it loads and the kernel itself, like the NVIDIA GPU drivers, are now a single point of failure. So container escape is not just a local privilege escalation problem, it's a cloud-wide breach issue. And while some providers have architected properly to avoid containerization as a cloud-wide security boundary, many have not. So remember the explosion of GPU providers that I mentioned? Well, the majority of them are not very mature security-wise. And even of the more mature cloud providers like GCP rely on something called gvisor, which emulates the kernel into user space. However, gvisor does not implement the NVIDIA GPU drivers, so they're still vulnerable to a lot of NVIDIA driver exploits. Now we'll actually demo our exploit, which takes over an Azure serverless compute node. So here I am queuing up the training job in the AI ML Azure workspace panel, and I'm loading some code that it will run into a container. That code actually just gets us a reverse shell, and we're queuing it up to run on a serverless GPU node with the container environment of our choosing. I chose TensorFlow, but it doesnn really matter. So here we get a reverse shell into the container, and we'll see here that we are trapped into a container. I'm running ps-ox, and we can see that the first process is an execution wrapper. Now we run the NVIDIA GPU exploit, and that exploit actually gets us another reverse shell outside of the container. And we'll see here in a second that we have a root shell onto the host compute node, and we will verify here in a second that we can see all of the processes on the host, and we can actually see co-located training jobs that were queued up by other users.
Awesome. Thank you very much, Valentina. So what you guys just saw is what I believe to be the first public exploit of the NVIDIA CUDA driver stack. And what we're going to do next is investigate exactly how that exploit works, starting with the vulnerability that we use to make it all happen. So this vulnerability is a race condition in this function called NVIDIA unlocks ioctl. And NVIDIA unlocked ioctl, it implements the ioctl system call for one of the character devices in the NVIDIA stack. And what it does is it takes in an array of 32-bit integers that represent GPU identifiers, and it allows the ioctl rather, it allows a file descriptor for that character device to hold references to a GPU. And so the name of the ioctl itself is called NVIDIA Escape Attach GPUs to FD, and we're going to take a closer look at exactly how it works. So the first thing that this ioctl does is it checks to see that the array that you pass in has a non-zero size, and that the size of the array is a multiple of 4 bytes, as to prevent an out-of-bounds read. The other thing that this check does that's important is that it checks to see that no GPUs have already been attached to this file descriptor. And this will become important in just a second here. Provided this check passes, the next thing the driver is going to do is it's going to allocate a buffer of a user-controlled size, arg size, that we pass in, and then it's going to copy data from another user-controlled source called arg copy, and it's going to copy that into this variable attached GPUs. This is actually where the main problem is. This variable, NVLFP, is short for NVIDIA Linux File Private, and it is allocated per file descriptor, and it's allocated on the heap. This means that this ioctl is capable of racing against itself because it is locklessly writing, as NVIDIA unlocked ioctl would suggest. It is locklessly writing to a variable on the heap. And so we have this very tight race window between where we can kind of pass this time of check here, that if statement, and while the kmalloc, which is NV kmalloc here, and that memcopy is occurring, and before that assignment at the bottom, we can kind of form a race which is going to make this attached GPUs variable very racy. Now, this alone isn't really enough to form a very strong exploit, much less a reliable one. And so while we have this time of check here, we're going to need to investigate the time of use. And so what that looks like is immediately after the code on the previous slide, what the driver is going to do is it's going to iterate through every element in that array that we pass in. And for every non-zero GPU ID, we are going to, or the driver is going to try and grab a reference with this function called NVIDIA dev get. And then if any of those function calls fail, what the driver is going to do is it's going to iterate backwards in that while I minus minus loop. And for every reference that it grabbed, it's going to release that reference with NVIDIA dev put. And this is quite important because the attacker, the malicious user space process, we can actually control the number of loop iterations that occurs because we can control if NVIDIA dev get fails. And this is going to be important for formulating the race semantics later. The other thing that the driver does in the failure case is it calls NVK free on the attached GPU's variable. And then it's going to reset the number of attached GPUs back to 0 so that you could reattach again should the need arise. And there's actually quite an important line of code missing here, namely that the driver does not reset the attached GPU's variable back to null, which means that this is actually going to form a double free of the attached GPU's variable. And this is quite important and actually an extremely powerful primitive because the attacker controls the size of the attached GPU's variable, and it's given by argsize. And argsize is anywhere between 4 bytes at the smallest and 16 kilobytes at the largest. And so this is going to form an extremely powerful kernel double free primitive. The other way to kind of exploit this bug that's a little bit trickier that we're not going to show is you can actually kind of mess with the reference counts of the GPUs here in this NVIDIA dev get and dev put loop. And the way that you can do that is since the attached GPU's variable is racy, you can kind of change what the buffer is behind the scenes while this loop is occurring. Although this is extremely difficult to control, it does lead to exploitable behavior, but it's really kind of extra credit on the homework assignment. So what we're going to be doing for the rest of to build our exploit is we're going to be working with that double free. And if at any point you kind of got lost in this race condition nonsense, 2 threads thing that's going on, the long story short of it is that we have a double free of any heap object of any size. And really, the only question left on exploitability is, can we get this race condition under control? And that's exactly what we're going to do next. But before we get started in that, we need to be concerned about what mitigations and defenses the kernel has in place for double free bugs. And kind of the main one we need to be worried about is this kernel config here called config slab free list hardened. And what this mitigation does is if the pointer that you pass to kfree is the same pointer that would have been allocated by kmalloc, then the kernel is going to panic or crash. And so this is quite problematic because if we cannot have an allocation occur between our race window, if we cannot guarantee that, then the kernel is going to panic and this will count as a failed attempt for pwn to own, which we only have 3 of. So this kind of leaves us with 2 choices. For one, is there some way that we can guarantee that an allocation occurs in that race window? Free would also work. Or the other alternative is, can we avoid this code altogether? And actually, it turns out there is a way to avoid this function altogether. And the way that we do that is that we can use a large kmalloc. And so a large kmalloc is anything over 8,192 bytes. And what it's going to do is it's going to directly invoke the page allocator as a result. Now, the page allocator is the physical memory allocator in the Linux kernel, and it measures its allocations in this unit called orders. And so an order is a power of 2 multiplied by the page size. So an order 0 page is going to be 4 kilobytes. Order 1 is 8K, 16K, 32K, and so on. And so this is important for our particular exploit because the size constraint we have is anything smaller than 16 kilobytes. So we need to be larger than 8K in order to hit the large kmalloc code. And then we need to be, we are constrained to be smaller than 16K, which means that we can allocate exactly order 2 pages and double free exactly order 2 pages and order 2 pages only. The other thing that's kind of interesting about physical memory allocations is that they're ref counted, unlike the virtual memory allocations made with kmalloc. So within the case of the double free, the reference count would originally fall from 1 to 0 on the first free, and then from 0 to -1 on the second free. So this kind of begs the question, what does the kernel do when it sees a page with a -1 reference count? And it does this. And if you've done kernel exploitation before, you might think, wow, that looks a lot like a crash. That looks like a lot like a kernel panic. But you'll notice that there is a line in that code missing, which is kernel panic not syncing. And believe it or not, this is actually just a warning message. You can actually do this millions of times, and the kernel will just kind of go, oh, that wasn't supposed to happen, and it's just going to move on. And so this is extremely important for our exploit because this logic is going to mean that our race condition is safe to retry. So now that our race condition is safe to retry, let's actually begin diagramming it out. So what I have here on the screen is I have 4 CPUs that we're going to perform a set of actions with over time. And those 4 CPUs, starting on the left, is the fast CPU. That's going to be doing the first free of the double free. And then I also have the slow CPU, which is going to be doing the double free of the double free. And then I have 2 spray CPUs, which are solely responsible for trying to allocate a bunch of memory such that an allocation occurs between the first free and the second free. So the first thing I'm going to do to trigger this bug is I'm going to ioctl into that vulnerable NVIDIA ioctl at the same time on my 2 racing CPUs, fast CPU and slow CPU. Following that, because we can control the number of iterations in the loop in the race condition, I'm going to have fast CPU exit very early and do its first free. And when I see fast CPU come back into user space, I'm going to start spraying memory. And that's in order to allocate a bunch of physical pages before the double free happens. When we see that, we're going to reclaim that memory as an order 0 page. Part of that is because we have a very nice aggressor object that uses order 0 page. And part of that is just because from user space, it's much easier to spray order 0 pages than it is pages of higher orders. Following that reclaim process, that allocation process, the slow CPU is going to double free, and then it is going to exit back in user space, and then we'll have some kind of dangling reference, dangling physical reference that we got from the reclaiming process. And this works pretty well, but it's important to note that if something happens out of order, such as that reclaim happening too late, the kernel is unhappy, but it's not going to panic. And so the other thing that is, while this does technically work, I said it worked pretty well earlier. I was kind of lying to the crowd here. The success rate of this is actually far beneath 1%. We can retry it, but importantly, the Pondon guidelines say that you need to complete your exploit within 10 minutes, and we want something a little bit more robust and reliable before maybe going to Berlin or missing the Berlin deadline by 2 hours. To begin kind of diagnosing some of the problems with this original model, we need to take a deep dive into the physical memory allocation process of the Linux kernel. And so here we're going to walk through what one of the spraying operations would look like for one of the CPUs trying to allocate an order 0 page. And so every CPU in the Linux kernel, for its physical memory allocation process, it's going to track a per CPU free list. And that per CPU free list is going to maintain a small number of pages for a small number of orders. In this case, it's orders 0, 1, 2, and 3. And so if the per CPU free list happens to have the right page for that order, fantastic, we're done. This is the fast path. If the kernel per CPU free list does not have that page, what the allocator is going to do is it's going to look inside of these global zones. And these global zones are going to have a lot more pages and a lot more orders. So if it happens to have the right order page in the global zone, fantastic, we're done. But really what we want is we want that third allocation path, which is shown here on the screen, where the allocator looks for a higher order page that it happens to have. In this case, I've shown the allocator being out of order 0 pages in the global zone and out of order 1 pages. And it's going to take a higher order page and break that down as powers of 2. In this case, an order 2 being broken down into 2 order 1 pages and then further being broken down into 2 order 0 pages, which would get returned to the caller. And so this is exactly what needs to happen in our race condition process, but there's kind of a problem in this diagram. And that problem is that our order 2 page from our NVIDIA double free bug can get stuck in this per CPU free list. And so if this is the case, there's no matter how much memory that we try and spray, we're never going to reclaim that page. And so the good news is that while this problem is kind of tricky and annoying to diagnose, and it took us quite a while to do so, the fix for this is actually quite easy. So before we start spraying, what we're going to do is evict or flush that per CPU free list, and that affects our timing diagram a little bit like this. So after the first free ioctl exits back into user space, but before we start spraying, we're going to introduce a new process where we evict the per CPU free list, and then once that is done, we will start spraying, reclaim the page, form the double free. And in this way, the order 2 page from our NVIDIA double free bug is going to be broken down into an order 0 page that can be used for exploitation. Now, this works a lot better. It actually works very well on emulator and emulator setups. But when we begin working with this on the Azure instances, it works quite poorly. And the reason why it works quite poorly is because the double free is happening immediately after the first free, and we're just trying to do too much stuff inside of this tight race window. And so to fix this, we opt to use a well-known technique to extend race windows, originally described by Jan from Project Zero, which is this very simple, very beautiful technique where you set a bunch of hardware timers and have those hardware timers just go off during a race condition, and it slows everything down, and it's perfect. And so when we implemented this technique, we saw that the race window grew by nearly 2,000 times, from 20 microseconds to nearly 38 milliseconds. So this is very, very effective. And so when we add this to the timing diagram, we have all of those timer FDs, all of those hardware timers be processed on the slow CPU. This is going to delay that double free process and give us time to perform the page eviction and reclaim the page and create that dangling reference. And so this is actually the final timing diagram. It's worth noting that what I had here on the screen is I have these events in bubbles and X's. The bubbles events, they happen in user space, and we know exactly when they happen. The events in X's happen in the kernel, and while we don't know exactly when they happen, they can happen in any, out of order in any way, and the kernel is going to be fine. We can still retry the race. However, for the rest of this exploit, we're going to assume that this timing diagram happened, and we have a dangling reference given to us by one of the Spray CPUs. So what exactly is that dangling reference? Well, it's this kind of this data structure that's very well known in kernel exploitation called the pipe buffer. And the pipe buffer is kind of the backing Linux implementation for Unix pipes. And frankly, it's kind of broken for kernel exploitation. I don't expect it to survive the way it is for much longer. But the reason why the pipe buffer is so nice in our exploit is that it holds a physical reference in its first field. And that physical reference is that struct page pointer page. And so the other thing that the pipe buffer does that's so nice is it provides a very easy way from user space to read and write to that physical reference. And so within the context of our race condition, what we did is we sprayed a bunch of pipes, and now we have one of those pipes where its struct page pointer has a reference count of 0 instead of 1. And so now that the race condition is complete, we can begin looking about how we turn that dangling reference into a proper exploit. And so the first thing we're going to do for that is we're going to create a physical memory type confusion. And so right now, what we do is we kind of we create this physical type confusion with this KMalloc 192 slab. And so before going into this, the double free pipe had a reference count of 0, like I had just said. We'll very quickly reclaim that memory again as a KMalloc 192 slab. And in this way, the page pointer inside of the pipe buffer points to the same physical address of this KMalloc 192 slab. And without going into a ton of details about how the KMalloc heap works, you can kind of imagine the KMalloc 192 slab as just one order 0 page, that's 4,096 bytes, with a bunch of 192 byte objects all adjacent to one another. And so the way that we kind of begin to weaponize this type confusion is the first thing we want to do is we want to bypass KSLR. And while we can kind of read as many times as we need outside of this KMalloc 192 slab, what we can do is we can actually move the doubled free pipe inside of the KMalloc 192 slab. And that's going to help us effectively bypass KSLR, and it's going to kind of lead the way into turning this into an arbitrary read-write primitive. And so to kind of set up the arbitrary read-write primitive, this is how our heap is going to look. And so we'll have the double free pipe on the KMalloc 192 slab. Its struct page pointer is going to point to the start of the slab, which, by the way, was filled with pipe buffers as a part of our heap spraying process during the race condition. And so we'll use this double free pipe, which is kind of working in a out of bounds read and out of bounds write kind of fashion. And we'll use it to corrupt one of the other pipes living on this slab. And what we'll do is we'll point that corrupted pipe to the start of the KMalloc 192 slab as well. And then what we can do is we can use that corrupted pipe to repoint the double free pipe to anywhere in kernel memory that we need. And then arbitrary read and arbitrary write is as simple as just using the read and write system calls on the double free pipe. And that's going to allow us to read and write arbitrary kernel memory anywhere that we need. And so with an arbitrary read-write setup, it becomes fairly easy to do escaping the container and local privilege escalation. And the way that we do that is we're going to corrupt this task struct structure. And in Linux, task struct represents kind of all of the privilege and sandboxing information of a given process. And so what we're going to do very simply is copy all of those fields shown on the screen from the task struct that's given for the init process, which on most operating systems is systemd. And we're just going to copy that over to our process. And in this way, we are going to perform local privilege escalation. We're also going to escape the container. This is also the same technique that was used in the Azure demo video. And it works quite well. This is going to work on Ubuntu, on Red Hat, on Azure, I believe on SageMaker as well. And it's fairly complete. But we kind of wanted to take this vulnerability a step further. This is a very kind of wonderful primitive that NVIDIA has given us, and it's actually powerful enough to fight the final boss of kernel exploitation. And the final boss of kernel exploitation is this instance called mitigation v4, which is specifically made for kernel CTF. And what mitigation v4 does that's so annoying is it has this non-mainline kernel config called config/virtual that makes type confusion-based attacks very, very difficult to exploit in the Linux kernel. And the way that config/virtual works is that when a kernel API calls kmalloc and the virtual memory allocator /virtual is out of memory, it's going to reach out to the page allocator to get more memory. And it does that with this call alloc pages. Then what's so annoying for kernel hackers is that when the page allocator returns that new memory, what /virtual is going to do is it's going to assign a unique page table entry to that memory. And it does this in such a way that no matter what system of allocs and frees that you have, memory from a pool like kmalloc 192 will never overlap with memory from kmalloc 256 or 512 or 1024. And this makes type confusion-based attacks very difficult. However, because our race condition kind of mandated that we use large kmallocs anyway, very interestingly, config/virtual does not assign page table entries to large kmallocs. And so since we're interacting with directly with the page allocator anyways, we can kind of just ignore most of what config/virtual does. And in fact, it's going to cause some very minor conveniences later, but it's really not going to get much in the way of this exploit at all. There are some other mitigations in mitigation v4. We just kind of ignore them. Actually, kind of counterintuitively, they make the exploit more reliable, but enough on that. We can begin to kind of diagnose or look at how this exploit works as a whole. So kind of what we did on our journey throughout this presentation. We started with this race condition, and this is actually where the bulk of this work was. So we strategically caused a double free in the physical memory allocator and ended up creating a dangling reference as a pipe buffer page and eventually reclaimed that as a slab. That reclaiming process formed a physical type confusion where we had a large kmalloc 192 slab that was filled with pipe buffer objects, and then we moved the double free pipe inside of our heap, and that allowed us to effectively bypass KSLR. From there, we did a little bit of memory corruption on the kmalloc 192 slab, and that allowed us to form this arbitrary redirect primitive. Now, config/virtual does somewhat get in the way here because it's assigning all these page table entries. It makes it kind of difficult to write to objects on the kernel heap, such as the task struct that I mentioned earlier. However, we still have kind of unrestricted control over kind of the main kernel image, like the .text, .data section. And also, the kernel memory is very low entropy at boot. So a large number of objects are at fixed locations in physical memory, which is kind of what this arbitrary read-write is doing. So really, mitigation v4, it's kind of annoying, but we're still fully capable of getting to LP and container escape. So this kind of mitigation for defeat is not new. Using large kmallocs has been very successful in terms of defeating mitigation v4, including I'd like to highlight a very wonderful presentation done by Theory actually at Hexacon last year. If you have not seen it, I highly recommend it. It was a wonderful talk on the heap shaping involved in the physical memory allocator to make an out-of-bounds write work. However, a lot of folks are using large kmallocs. A lot of folks are using page-level attacks, which kind of shows the efficiency and the how effective actually that config/virtual is. Because a lot of folks really haven't really bypassed it per se, but really just worked around it. So that actually kind of wraps up our presentation here today. I'd like to give thanks to a few folks on the screen, starting with the folks at IBM, Fabius, Ruben, and Chris, who without their help this presentation would not have been possible. I'd like to thank the Hexacon organization team, Synactive, the review board, for hosting this amazing, amazing conference and inviting us to speak. As I mentioned before, the research team at Wiz is doing phenomenal work, including actually successfully making the Pwn Berlin 2025 deadline with their NVIDIA Container Toolkit Escape. And then finally, the kernel CTF community and the Pwn contest as well. As we kind of seen throughout the last few days at this conference, they are providing incentives for a lot of research in the public domain, including ours. And they're really, really pushing the security community as we know it. So with that in mind, I'd like to share this one other bug from our report to NVIDIA. This was actually only disclosed 2 days ago. And this is a heap overflow / null pointer dereference. And so if you're kind of interested in GPU driver exploitation, neither myself nor Chompy were able to actually successfully exploit this bug. So it only takes 2 lines of Python code to get started, and you can show us up at the same time. So with that in mind, if we have time for questions, then we'll be happy to take those. Otherwise, thank you guys very much for coming, and I hope you enjoyed the talk.